Chapter 3, Differentiation Rules, Section 3.1, Derivatives of Polynomials and Exponentials. The derivative of a constant function, f of x equals c, is 0. So that means that we apply d dx to any constant c, we get 0. For a proof, if we have f prime of x, remember that's equal to the limit of f of x plus h minus f of x over h, as h goes to 0. So our constant is a function, so that means that f of x is the same as f of x plus h. Plugging in anything isn't really plugging in anything. So we end up with c minus c in our numerator, which is just 0. So our limit is 0. Similarly, we could prove that the derivative of x is 1, the derivative of x squared is 2x, derivative of x cubed is 3x squared, and the derivative of x to the fourth is 4x to the third. Pretty much the same fashion, just use the definition of derivative. For our next theorem, the power rule, if n is a positive integer, then the derivative of x to the n is just n times x to the n minus 1. So that means that you take the exponent, you make it hop down in front, and you just reduce it by 1. So if, it's like over here, we had x squared, the 2 hops out and becomes a 1. Over here we had 3x x cubed. 3 hops out, becomes a 2. Okay, so let's do this proof. You might recall that you can expand binomials of the form x to the n minus a to the n by factoring out x minus a, and then everything left inside is 1 power lower. So we take out one of the x's. We have x to the n minus 1 plus x to the n minus 2 times a, and so on. So that means that if we wanted to take the derivative, that would be the limit of f of x minus f of a over x minus a. So in this case, f of x is x to the n. That's what we're trying to take the derivative of. So f of a, we just plug in a, it's a to the n. So our numerator is this thing that we just expanded. So that means that we can, remember this thing is equal to this whole mess. So it basically, we're plugging that in the numerator, and then we have an x minus a on the top and an x minus a, an x minus a on the bottom and an x minus a on the top. So those will cancel because we're only going near a, not equal to a. So there's no possibility of the denominator being 0. So then we're left with just this in our numerator. And that's a polynomial, so we can use direct substitution for the limit. We just plug in a. So instead of x to the n minus 1, it becomes a to the n minus 1, and so on. So then when we multiply a to the n minus 2 times a, it becomes a to the n minus 1. And similarly, when we multiply this a by a to the n minus 2, it becomes a to the n minus 1. And for every single one in between. So that means we end up with a to the n minus 1 plus a to the n minus 1 plus a to the n minus 1, and so on, n times. There are n of those. So having n of the same number being added, adding the same number over and over and over again n times is the exact same thing as just taking that number and multiplying it by however many times you're adding it. So that's n times a to the n minus 1, which is what we wanted to prove. Okay, let's use that. Let's find the derivative of x to the 6th. So the 6 hops out in front, and we get f prime of x is equal to 6 times x, and now we just reduce the exponent by 1, so instead of 6 it becomes 5. Okay, for the next one, the derivative y prime, 1000 hops out in front. We end up with 999 as the exponent because it goes down 1. For the next one, if we want the derivative, dy dt, that equals 4t cubed. 4 comes out in front. And for r cubed, how about we write it as the derivative ddr of r cubed is equal to 3r squared. Notice we have 4 different types of notation here. They all mean the exact same thing, just take the derivative. Okay, so we actually have a general version of the power rule. Notice for the one that we proved, we said that n had to be a positive integer. But the power rule is actually more powerful. It works for any real number. We're going to prove the more powerful version later, but we'll start using it right now. So n, that exponent, could be any real number right now. So we can plug in any crazy number, like a half or a third or anything we want. We can still do the power rule. So let's differentiate something like 1 over x squared. So f prime of x, that's equal to the derivative of x to the minus 2 power. So remember that dividing when you have an exponent is the exact same thing as moving that exponent into the numerator and making it negative. So now we have it in the form of a power function. So we can apply the power rule. So the negative 2 hops out in front. And instead of being x to the minus 2, we have to go 1 lower. So it becomes x to the minus 2 minus 1. Simplifying, we get that that's equal to x to the minus 3. Okay, and now we can return it to fraction form by putting that in the denominator. So negative 2 stays in the numerator, x cubed goes to the denominator in order to make the exponent positive. If we want to take the derivative of the cube root of x squared, that's the same thing as the derivative of x to the 2/3 power. So now we just make the 2/3 hop out in front. So we keep 2/3 and we subtract 1. So that's 2/3 x to the minus 1/3. Okay, the normal line to a curve C at a point P is the line through P that is perpendicular to the tangent line. So whatever we find for the tangent line, we just find another line perpendicular if we want to get the normal line. Alright, let's find equations of the tangent line and normal line to the curve y equals x square root of x at the point 1, 1. Okay, remember that finding the equation of the tangent line relies on finding the slope of the tangent line, which is equal to the derivative. So we have f of x equal to x square root of x. We want to apply the power rule, so we can make this into x times x to the 1/2, so that we can get an exponent in there. And then x to the 1 times x to the 1/2, add the exponents, x to the 3/2 is what it becomes. So then we've got our derivative equal to 3 over 2 times x to the 3/2 minus 1. So that's 3 over 2 times x to the 1/2, which is 3 over 2 times square root of x. Okay, we want the slope of the tangent line at the point 1, 1. So that's at x equals 1. So we're looking for f prime of 1. Well, plugging in 1 for x, you get square root of 1 times 3 over 2. So that's just 3 over 2. Okay, so we can write our tangent line now. That'll be in point slope form, y minus our y value of 1 equals m, our 3 over 2 for our slope, times x minus our x value of 1. And we can simplify that into y equals 3 over 2 times x minus 1/2. for our normal line. Remember, it's the exact same thing as our tangent line, except that the slope will be different because it's perpendicular. So instead of 3 over 2, we have to make it the negative reciprocal, so it becomes negative 2/3. Okay, that's the same thing as saying y equals negative 2/3 x plus 5/3. Okay, next up we have our constant multiple rule. If we have the derivative of any function times a constant, then we could just take that constant and pull it right outside, and then proceed with our derivative, kind of like we did with our limits. Okay, so let's prove this using the definition of the derivative. We want to do, want to let g of x equal a constant times f of x, and then look at what g prime of x is. So we look at g of x plus h minus g of x over h by definition. And g of x plus h is just c times f of x plus h. And then g of x is just c times f of x. Because this is the limit of a constant times something, we can just take that constant, factor it out from our numerator, and then pull it out of the limit. And then once we do that, what's left inside the limit is just the derivative of f. So we proved it. Okay, let's find these derivatives. Derivative of 3x to the 4th. So we can use our constant multiple rule, pull out the 3. So this will be 3 times the derivative of x to the 4th, which is a power function, so that's just 3 times 4x to the 3rd. So it's just 12x to the 3rd. Similarly, derivative of minus x is the derivative of minus 1 times x. Since minus 1 is a constant, we can pull that out. So it's minus 1 times the derivative of x, which is just minus 1 times derivative of x is 1. So this is just minus 1. Okay, next up we have our sum rule. Similar to limits, the derivative of a sum is the sum of the derivatives. Okay, and we can prove that. Let big F be small f plus small g. Then the derivative of big F is big F of x plus h minus big F of x over h. We plug in for big F of x plus h, and that's f of x plus h plus g of x plus h. And then big F is f plus g. So then we want to split our sum. Because it's over a common denominator of h, we can make it f of x plus h minus f of x. Just change the order, move that over a little bit, and you get this left sum. And then do the same thing over here, move this over a little bit, and then you get this right sum. And then the limit of a sum is the sum of the limits, so it splits into this limit and this limit, which are just the derivatives that we wanted. Okay, you can prove the difference rule the same way. Derivative of a difference is the difference of the derivatives. So let's use some of these rules. Let's find the derivative of this polynomial. It looks terrible, and it would be terrible if we were using the definition of the derivative instead of using the power rule and the sum and difference rules and constant multiple rules. But in fact, with all of our rules now, this will be a cinch. So this thing is just the derivative of each of the terms. Derivative of x to the 8th plus 12 times the derivative of x to the 5th minus 4 times the derivative of x to the 4th plus 10 times the derivative of x to the 3rd minus 6 times the derivative of x plus the derivative of 5. Okay, so for our first guy, derivative of x to the 8th is just 8x to the 7th. Then we've got 12 times 5x to the 4th. Then minus 4 times 4x to the third plus 10 times 3x squared minus 6 times 1, and derivative of a constant is 0, so plus 0 for the 5. So that equals 8x to the 7th plus 60x to the 4th minus 16x to the 3rd plus 30x squared minus 6. Let's find the points in the curve y equals x to the 4th minus 6x squared plus 4, where the tangent line is horizontal. So we're looking at the tangent line, we want to find the slope of the tangent line, so we want to find the derivative. So let's look at dy dx. So that's d dx of x to the 4th minus 6 times the derivative of x squared plus the derivative of 4, but that won't matter. Okay, so that's 4x cubed minus 12x plus 0. So it's 4x cubed minus 12x. We can pull out the 4x, and we'll just get x squared minus 3 inside. We want to see where the tangent line is horizontal. So horizontal lines have a slope of 0. So we're looking for where the slope is 0, which means that we're looking for the derivative is 0, because the derivative is the slope of the tangent line. So we're looking for where the derivative is 0. So notice that that's when this thing is 0, which happens when either this guy is 0 or this guy is 0. So either x is 0 or x squared minus 3 is equal to 0, which means that x is equal to plus or minus rad 3. Okay, so the tangent line is horizontal at 0, 4, because if we take x equals 0 and plug it in to y, we get, plug it into where x is to get the y value, we get 4. If we plug in square root of 3, we get minus 5. And if we plug in minus square root of 3, we also get minus 5. Okay, if you were to graph this thing, it would look something like this. Very loosely. We should have a horizontal tangent line over here. That's at minus rad 3 minus 5. We should have a horizontal tangent line over here at 0, 4. That's this point over here, this point over there, and last point to be over here at rad 3 minus 5. The equation of motion of a particle is s equals 2t cubed minus 5t squared plus 3t plus 4, where s is measured in centimeters and t in seconds. Find the acceleration as a function of time. What is the acceleration after 2 seconds? Okay, in order to find acceleration, remember that's the second derivative of position. It's the derivative of velocity, which in and of itself is the derivative of position. So our position is s. Our velocity, v, is the derivative of s, ds dt. And then next we'll differentiate that to get our acceleration. So when we differentiate 2t cubed, we get 6t squared. When we differentiate 5t squared, we get 10t. And when we differentiate 3t, we get 3. And when we differentiate 4, we get 0. So that means that the velocity is that function, and the acceleration is the derivative of velocity. So instead of ds dt, this will be dv dt. And that's derivative of 6t squared is 12t. And the derivative of 10t is 10, so minus 10. Okay, we want to know acceleration after 2 seconds, so that's a of 2. So we just plug in 2 for acceleration for t, and we get that it's equal to 14. And this was in centimeters, so that's centimeters. It's not per second because we differentiated twice. It's the rate of change of a rate of change. Velocity would have been centimeters per second. Position is centimeters. Velocity would have been centimeters per second. So acceleration is centimeters per second. So it's centimeters per second squared. Okay, next up, we want to define the number e. In order to motivate this, how about we take a break from our notes for a second and try finding the derivative of the exponential function. So if we let f of x equal b to the x for an arbitrary exponential function with base b, then our derivative, by definition, is equal to a limit of f of x plus h minus f of x over h. So we just plug in b to the x for that. So f of x plus h is b to the x plus h. And b to the x is, sorry, f of x is just b to the x. Okay, so we have b to the x plus h by our laws of exponents. That's just b to the x times b to the h. And then we still have our minus b to the x over h. So that means that we can factor out b to the x because it's in 2 places. So that's b to the x times b to the h minus 1 in the numerator. Okay, so you have to be a little bit careful here. Notice that this is the limit as h is going to 0. Not x going to 0, h. So that means this entire term b to the x is completely independent of h. As far as h is concerned, it's actually a constant. Even though we know it's not a constant because x is a variable, but as far as h is concerned, it is a constant. So as far as the limit is concerned, it's a constant, so you can pull it out. So that means that this is b to the x times the limit of h, the limit of b to the h minus 1 over h as h goes to 0. Okay, so notice that this is actually a very interesting limit. We already know what this limit is. This limit is the same exact thing as the limit of b to the 0 plus h, right? 0 plus h is h. And then instead of minus 1, I could write this as b to the 0. So look at how that compares to this limit. It's the exact same thing except that x is 0. This limit was the derivative of x. Sorry, the derivative of f at x. So this limit over here is equal to the derivative of f at 0. So we have b to the x times f prime of 0. It's that derivative. This entire limit is the derivative of the function in disguise, but at the point 0. Okay, so that means that if I look at the function b to the x, exponential function, and I take the derivative of it, I get the function itself times its own derivative at 0. So then you might ask, okay, well, wouldn't it be awesome if its own derivative at 0 happened to be 1? Because then when I took the derivative of b to the x, I would get b to the x times 1. I would just get itself, no matter how many times I took the derivative. So let's use that to define e. I want this limit over here, which is the derivative at 0. I want that limit to be 1. So let's take b, and let's let that equal e, where e is whatever number happens to exist that ends up forcing that limit to become 1. So it turns out that that number actually does exist. You could do a bunch of calculations, try doing the limit at b equals 2, try doing the limit at b equals 3, and then try going closer and closer to around 2.7 whatever. And eventually you will see that the limit is 1, experimentally. We're also going to do alternative definitions for e later, but this is the one we're going to use right now. So e is the number such that this limit is equal to 1. As we just saw, that forces the derivative of e to the x to be e to the x times the derivative at 0, which is just itself. It's just 1, so the derivative will be just itself. So the way that we defined it, e is the constant such that e to the x ends up with its own derivative. Okay, let's do an example. If f of x is e to the x minus x, let's find f prime and f double prime. Well, f prime of x is equal to the derivative of e to the x minus x, which is just a difference. So we can use our difference rule to take the derivative of e to the x minus the derivative of x. And I just said the derivative of e to the x is e to the x. And we already know the derivative of x is 1. For our second derivative, that'll just be the derivative of e to the x minus 1. So that's just the derivative of e to the x minus the derivative of 1, which is 0. So it's just e to the x. Notice that you can take the derivative of e to the x as many times as you want, and you'll still have e to the x left, but taking the derivative of x enough times gets rid of it. So if we take the derivative of a polynomial enough times, we'll end up with 0. Okay, let's look at what point on the curve y equals e to the x is the tangent line parallel to the line y equals 2x. Remember that parallel lines have the same slope, so we should look at the slope of the tangent line, which conveniently is the derivative. So we have y equals e to the x. So the derivative y prime is equal to e to the x, because derivative of e to the x is e to the x. We also know that that's the slope of the tangent line, m, and we want this slope of the tangent, we want the tangent line to be parallel to the line y equals 2x, so we want it to have the same slope. Notice for y equals 2x, the slope is 2. So we want m to be equal to 2. So we want e to the x to be equal to 2. We take the natural log of both sides. We get that x is equal to ln of 2. So that's our x value. That's half our point. We plug ln of 2 back in. So this tells us that y is equal to e to the ln 2. E to the ln cancels and gives us 2. So our point is an x value of ln 2 and a y value of 2.